In our previous video, we look at what is the amplitude of a signal, what is frequency of the signal. If you don't have access to this video, you can check our videos and learn what is the amplitude and what is a frequency of a signal and why they are important in the analysis of signal in courses such as the electrical engineering. Now we will look at what is a phase of a signal. If you want to understand fully what is a phase, you can watch this video till the end. And after this video, I believe you should be able to know what is a phase of a signal. In our previous video, we defined a signal which is alternating given with this equation, which is the amplitude or the voltage peak of a signal sine 2 pi the frequency time plus or minus the theta. And from a waveform, from a sine waveform, we describe the amplitude of a signal as the voltage peak of a signal, and we give the relationship between the frequency and the period. So the period is given as a time taken to complete one cycle. Therefore, the frequency is inversely proportional to the period. If you know the period of a signal, you can calculate frequency. And if you know frequency of a signal, you can calculate a period. So this is the voltage peak and this is a frequency of a signal. And now we will discuss this parameter which is known as a phase. Before we go into understanding a phase, this signal Vt, which represent the AC signal, which is Vp sine, it can also be represented as omega t plus or minus the theta. Now omega is called the angular frequency, and this angular frequency is given as 2 pi df. When we talk about the angular, we are talking about a phasor form. Why do we say it is a phasor form? And it is correspond to the term which is the frequency. So it's the phasor representation of a frequency. And we all know that a frequency is a time taken to complete one cycle of the wave. And this graph represents nothing but our waveform. To understand what is a phasor and why it is mostly used in AC signal, we will now see a diagram that will clearly show us why a angular frequency can be represented as a phasor form. From this diagram, you can see we have the sinusoidal waveform in the time domain, and this is the phasor representation of this particular waveform. And we can say the phasor diagram have some relationship with the waveform. And now you can see in terms of the phasor representation, to complete a one cycle, that means the frequency represent the time taken to complete one full cycle. And this waveform here is a representation of one full cycle. That means to find the frequency, we have one cycle over the time it takes to complete this one cycle. That means this represent the period, and the period represent the time it takes to complete this one particular cycle in an AC waveform. And we will discuss the phasor representation of this waveform and what kind of relationship they have. If you see from this diagram, this phasor representation is now representing each of the point in the AC. For example, a 30 degree, which can be represented in this point of a waveform. And this 60 degree phasor form can represent this portion of the AC signal. And for the 90 degree, we have the peak of the AC signal. When we go to 120, it represents this point in the AC signal. So we can see the relationship between the phasor and the waveform. To understand, we can simply summarize such that the phasor is mostly represented in the radian per second and corresponding to the waveform we measure in the degree. To show this relationship, we can see that 0 radian per second is equivalent to 0 degree, and if we say pi on 2 radian per second is equivalent to 90 degree, and pi rad per second is equivalent to 180 degree, and 2 pi on 3 rad per second is equivalent to 270 degree. And now you have the 2 pi rad per second is equivalent to 360 degree. From this last portion, when we say 2 pi f, which represent the angular frequency, that means this 2 pi represent a complete revolution of an AC signal. Therefore, for a particular frequency, we should have a 1 cycle in this regard, and we have the frequency of this cycle, and they all now represent the angular frequency of the AC signal. And we can see that this 90 degree is pi on 2, this point is pi, and this point is 2 pi on 3, and this point is now 360 degree. You can also use your calculator to compute those values by setting the calculator to a radian mode. When you understand each of these portions in the waveform, it is now easy for you to understand what is a phase in a signal. So this phase is normally come from the phasor representation of a signal. Now this will lead us to the definition of a phase. So what is a phase in an AC signal? We can now define the phase of an AC signal, which refers to the position of the waveform relative to a reference point in time. We can say the time is the reference time, which is 0, and it is typically measured in degree or the radian. The important thing to take away from the definition of the phase of an AC signal is the position of the waveform and the reference point in which the signal is measured, especially for, let's say, the time is equals to 0. So I will give you an example why we say a signal as a phase shift. Otherwise, in most of analysis, you will find that when we want to measure a single signal, that means we won't have a phase shift. But when we are dealing with multiple signal in an electrical circuit, we now will come across different signal which vary from each other. And to understand this relationship corresponding to the mathematical equation, we now have come up with the idea of adding shift as one of the key components in an AC signal. I will give you an example in which you can understand what is the phase shift and how you can calculate the phase shift of an AC signal with respect to the waveform. Let us look at some example. Now let us show you an example, Vt, which is a function of an AC signal, and we have the Vp sine, let's say 2 pi ft plus theta. Now we can substitute a value to make it more precise. So we say the function Vt is equals to 2 sine 2 pi ft plus 0. Now we will analyze the signal, and since it has a phase shift of 0, it can be simply written as 2 sine 2 pi ft. So now this will be our signal under consideration. So let me draw you this type of waveform. We can sketch this represent the Vt, this represent the time, and we can have 2 and minus 2. Now we can have the waveform which represent this equation. Now the starting point is when t is equivalent to 0. This waveform begin when t is equivalent to 0, and it will continue to oscillate for t approaches infinity. So it will continue to oscillate. And this type of signal now represent the equation given here. And what will happen if we now want to know what is a phase shift by adding the function Vt is equals to 2 sine 2 pi ft plus, let's say, 90 degree. Now from this waveform we can see 90 degree is the phase shift of the signal. And from the definition, we normally refer to the position of the waveform which has a reference point, for example at t or time is equals to 0. In that case, when t is equals to 0, we know that this waveform exists. And when we shift the signal, this particular signal by a 90 degree, what will happen? From this diagram given, we can see that 90 degrees is given in this area of the x-axis. Now, if we are to shift this signal, this point to the 90 degree, that means the signal will be different from the original signal because we are shifting the signal by a degree of 90. Now, if we want to draw the waveform to show this comparison, we now will have the same signal, which is Vt time, and we know that this signal must shift by a 90 degree. And from this figure, we can see that this point is the pi, this point is 2 pi, and this point here is pi on 2, and this point is 2 pi on 3. Now that means we have to shift by a 90 degree. Now if we are to say that this signal is pi on 2, this is pi, 2 pi on 3, and we have the 2 pi. The signal must be shifted by a 90 degree. That means in this region. So initially the signal starts at t is equals to 0. Now the signal will start from minus pi on 2. So you will now have the waveform. We have 2 minus 2. The signal will look something like this. And from this 90 degrees, it is a positive 90 degrees. So that means it will shifted to the left. And we can see the point of origin. Previously it is in here. Now it is shifted towards the left by a portion of 90 degree. That means it is in a phasor form of pi on 2 radian per second. if you want to shift a signal, if it is a positive value, we know that we have to shift towards the left. Now, if you want to shift by a 30 degree, that means this portion of the 30 degree must be shifted to minus 30 degree. Now, this will be appear in this region. And if you want to shift by 60 degree, that means you have this portion here. So you will have to shift all this portion to 30 and you have minus 60 degree. In that case, by shifting the signal per degree, we can now be able to shift according to this portion. So you can shift in any order of the phase. And by shifting the signal for a positive, we normally shift towards the left. And for a negative, we normally shift towards the right. And it is mostly defined in a term called advance or a delay in the waveform. And for the same example, if we have Vt is equals to 2 sine 2 pi ft plus 180 degree, then you all know that this part of a signal will now be shifted to the other side. Now we can be able to automatically draw this particular waveform. We can have minus pi and pi in this region. We can have 2 and minus 2, and now the signal will be like this. So we can see that the half of the cycle, which represent pi, is now shifted. So it can also be written as 2 sine 2 pi ft plus pi. And this represents the phase that is shifted with a plus sign, meaning it is shifted towards the left by 90 degree. And by understanding all of this, now we can see the difference. We previously said that we will use a sinusoidal signal for most of our representation in describing the AC signal. And we describe a sine signal and the cosine signal. Can you be able to see the difference between those signals? From this diagram, we can see that this one, we can say the sine signal, which is equals to 2 sine 2 pi ft plus 0, represent a sine signal. And this case, we have a sine signal which is equals to 2 sine 2 pi ft plus 90 degree or pi on 2. Now this sine signal with a phase shift of 90 degrees is equivalent to a cosine signal. So we can define that a cosine signal is a sine signal with phase shift of pi on 2, which is equivalent to a 90 degree. So a sine signal is a cosine signal, but with a phase shift of 90 degree. So this signal now, we can simply say it is a cosine signal. And it can be represented mathematically as Vt is equals to 2 cos 2 pi ft plus 0 degree. Now you see for this cosine signal, there is no phase shift. But you compare with the sine signal, it has a 90 degree phase shift. So a cosine signal is a sine signal with a 90 degree phase shift. So I believe with this example, you can be able to fully understand why do we mean by the signal phase. Every time when you shift the signal, depending on the plus, that means shifted towards your left, minus, that means towards your right. There are many applications that normally uses the phase shift. I will give you an example to show you the relationship between a voltage and a current in an electrical circuit. We all know that in an AC, we have the voltage and the current both alternating. But there are some components in an electrical circuit that will make the voltage and the current differ in an electrical circuit. I will quickly show you an example of we have VT and V1T, and we have V2T. In this case, if the signal is shifted by, we have minus pi on 2, and this is the point in which the signal begins, and it has a phase shift which is equivalent to 90 degree. Now we can say V2T is ahead of V1T. That means V2T leads V1T. And this is how you normally explain a signal. Because from the definition, we describe measuring a signal at t, which is equivalent to 0, which represent the reference. That means before the V1T begins, V2T already exists in advance. Therefore, it is leading the V1T. And with another waveform, we can have T, VT, and if we have example V1T, and we have the black represent V2T. Now we can say the phase shift is equivalent to 180 degree, and V2T and V1T are the mirror image of each other. Like what we have discussed in the previous example, we can see that if we are to continue in this region, this will be pi. That means if we shift V1T for 180 degrees, which is the pi, now we can say that it is shifted by 180 degree. That means V1T is shifted by 180 degrees, which now forms the V2T. And this is the basic analogy which will show you the difference between what we have explained previously. If you like our video, you can subscribe and share the video with your friends so they can be able to learn what is some of the key component of the AC signal. You can also click the notification bell. Whenever we upload new videos, you can be able to get notified of those videos.